So here's what we're doing in this section, probability and counting rules. We're taking what we learned in 4.4 in terms of how to find the number of something given a certain circumstance, and now we're going to find the probability of that happening. Okay, so we're going to combine the beginning of chapter 4 and its probability rules with the counting rules, permutations, and combinations. That's all that 4.5 is. Okay, so that being said, some of those problems at the end of your homework yesterday where you had sort of two groups of things to choose from, that's going to happen today. We're going to be looking at things like that and try to break them down. So, that's what I just said. We're going to use the counting rules to find our probabilities. And we're going to divide those possibilities, what we did in 4.4, by the total number of possibilities. So the same conceptual idea for probability exists. That doesn't change. It's just that we're going to use those formulas and counting rules to help determine the number of choices we're trying to come up with out of the total number of possibilities. Here's a problem. Find the probability of getting 4 aces when 5 cards are drawn from an ordinary deck of cards. So, getting a really good hand, right? 4 aces in poker is really good. How many of y'all play poker? Or have played poker before? How many know nothing about poker? Okay. Well, you're going to learn a little bit about poker today. Getting 4 aces is a really, really good hand. In fact, it's just about the best hand you can get unless you're playing with wild cards. Okay? And so, what that means is the probability of doing this should be really, really, really small. The same as we talked about the Powerball or the Mega Millions, the likelihood of winning it was really, really small. Getting 4 aces is really small too, and I'm going to show you how to come up with this. So I'm going to break this problem down into a bunch of different parts. Okay. Obviously, we need to talk about getting 4 aces. That's one part of it. But we have to have 5 cards. So we're going to also have to talk about the possibilities of getting that 5th card. So we're going to start with this idea of 4 aces. Okay. Does the order of the aces matter? No. Okay. So is this a combination or permutation? Combination. Okay. How many aces are there in a deck?
4.
How many are we going to select?
5.
There are only 4 aces.
Well, it's 5 cards.
Well, I know, that's a separate thing.
Okay.
So, of the 4 aces, we're going to select all 4 of them. Okay? So in order to write or figure out what we need to do in order to come up with 4 aces, we've got to take a combination of 4 things, and we choose 4 of them. Okay? That's the formula piece for the aces. Okay? We also have the 5th card. Alright? We have to choose how many cards now?
5. 1 more.
We're choosing 1 more card out of a total of how many?
52.
Nope.
48.
48. So this 5th card can't be an ace. So we've taken all the aces out. There's only 48 cards left. So the 5th card, there's only 48 cards left. And if you wanted to write it as a combination, it would be 48 choose 1, which is 48. Okay? But there's 48 cards left. So if you wanted to think about it like a slot, you could think about it that way too. Either one is fine. Now, this is for total possibilities. This is not probability. Right? This is just the top. The top is how to pull 4 aces in a 5th card. What we also need to do is figure out the total number of possibilities. Okay, because we're going to take that and we're going to divide it by the total number of possibilities. And then we'll be able to figure out probability. Okay, well, let's think about what the total possibilities are. What are we talking about? What's going to happen in order for us to determine the total number of possibilities? What's the context here? The total possibilities of what?
Drawing all 4 aces.
No.
Which card?
How many cards are we drawing all together? So the total possibilities is the number of ways that I can draw 5 cards from a deck. Okay? We're looking at a specific type of situation when we draw 5 cards. But the total possibilities are the number of ways I can draw 5 cards, period. So what's that going to look like?
Per number?
I'm looking for kind of like a formula. How many cards am I choosing? From how many? 52. So my total possibilities then is a combination of 52 choose 5. Because the order of the cards don't matter. Okay? So go ahead and do that calculation. This is a giant fraction, okay? This is a giant fraction right here. This is the probability of getting 4 aces. Here's what you've gotten when you simplified this out, okay? So the top is just 48. Combination of 4 things. When you choose all 4 of them, there's only one way to do that, okay? The bottom gives you 2,598,960, okay? Reducing that fraction means there's 1 out of 54,145 ways to do that. Okay? So one of the things that you have to be able to do, because I know some of you were going calculator crazy on this, which is fine, but you know, when we get to our test that's multiple choice and your responses are all in fractions, and you did it all in decimals, right? You've got to be able to work between both of them. How many people got that? Raise your hand if you got that, or you got the equivalent of that using your calculator with a decimal. I don't know. Why don't you figure it out? Divide it out and see what it is as a decimal. What is this as a decimal? Okay, so as a decimal,
That's right.
okay, should be like that as a decimal. Now, here's the other thing. In your calculator, some of your calculators, it'll look like this. Okay, this means 1.5 times 10 to the negative 5th. If you write this as an answer on your test, I'm not giving you any credit. You need to know what that means and be able to write it out. Okay? Again, most of your test is multiple choice though. So you need to be able to work between what's in your calculator, what it actually is, and potentially what fraction it is. Okay? So those are things I'm going to leave up to you to navigate. Okay? Unless the problem says, you know, work it through fractions, work it in decimals. You have the freedom to flow between that as you wish. Okay? I will tell you that most of the time when it comes to cards, we leave them as fractions. Okay? Are there any questions on that problem? All right. Let's make it a little tougher.
More?
Yep,
Difficult.
more. This is going to be, so this one has 4 parts. So you can take a picture of that if you wish. And we're going to work through all those parts together. So here's the thing. We have a box of 24 transistors. 4 of them are defective. We're trying to find out if 4 of those 24 are sold at random, the number of probabilities. So here's what we're trying to figure out in part A. We're going to pick 4 of these transistors. Exactly 2 of them are defective, which means 2 of them are
Not working.
2 of them are not working, and then the other 2 are totally fine. There's no issue with them at all. Okay? So we're going to choose 2 from the 4 that are defective, right?
I think we just
Okay, here's what it's saying. So you're going to pick 4 at random, okay? But of the 4, 2 of them are going to be defective, which means the other 2 are not defective. They're fine. That's the first situation. So here's what we're really talking about. We have 2 things that we have to pick from. We have 2 sort of piles that we have to pick from. We have to pick from the defective pile, which there's 4 of those. And then we have to pick up the not defective pile. How many are not defective? 20 are not defective. So we have to first determine how many different ways we can come up with 2 defective and 2 not defective. And then we have to divide that, because we're looking for probability. Then we have to divide that by the total number of ways there are to choose 4 transistors. Okay? So I want you to try to work through this a little bit and see if you can come up with this. And then we'll kind of talk through it and see if you did it right. Okay? So again, think about it this way. You're choosing from 2 different piles. You have one pile of the defectives that you're choosing from, and then you have one pile of the not defectives that you're choosing from. Okay? So try to write a formula. Don't at this point don't worry about the math so much. I want you to use the right combination or permutation formula first and set it up, and then we'll talk about it and make sure you're on the right track. Does the order matter?
No.
It doesn't. So these are going to be combinations, okay? So let's talk about the defective pile. How many are being chosen from how many here? 2 from how many? 4. So there's 4 defective. We're going to choose 2 of them. Okay, so that's the defective pile. Okay? You already told me there were how many not defective? 20. How many are we choosing from that part? 2. Okay? So the combination for the not defective is 20 choose 2. How many had those 2? Good. So then, what do I have to divide it by? How many total possibilities of choosing 4 transistors are there? 24 choose 4. Okay? So then I'm going to choose 4. So this is the total possibilities right here. Okay? So there's my fraction. That's how I'm going to come up with my probability. So now go ahead and do the math and see what you come up with. And I'm going to ask for it. Actually, you can put it in a fraction or a decimal. I don't care. I have both ready to go. If you did it right, mathematically, here's what you end up with. 4 choose 2 is 6. 20 choose 2 is 190. And 24 choose 4, 10,626. That's the first part of it. How many had that part of it right? Very good. Okay, now we have to simplify. Okay, and simplify that all out. And you could either get 190 over 1,771, which is approximately equal to 0.107. Okay? How you round it, I'm not going to get too hung up about. But again, when we get to the test, obviously you have to choose one of the right ones. And if it's a free response type question, I will tell you what you need to round to if you choose to round. Yeah?
I think if I washed my lanyard.
Oh my God. I want you to try B. Try to do B on your own. Let's see how you do. I think one of the things that confuses you about B is the idea of the word none. It would be better if it said 0 are defective, because we're still choosing from 2 piles. We're choosing from the defective pile, and we're choosing from the not defective pile, or the completely functioning fine pile. However you want to label it, okay? But the ones that are not defective are properly functioning transistors. Okay, so you're still choosing from those 2 piles or those 2 buckets. Okay? Just the fact is, when you say none defective versus not defective, that's not. It's zero transistors that are defective, and then how many transistors are you going to choose that are not defective?
0 or 4.
4. Okay? So essentially, we're not choosing any from the defective pile anymore. Okay? That's sort of what we eliminate. So when we look at this first one for B, the truth is we're only selecting from the functioning transistors. We're not choosing any from the broken ones, from the defective ones. So you could have put, if you wanted to, you could have also put from the defective pile, it's just not going to let me do it, choosing 0 of the broken ones from the 4, but that just is 1. Okay? The fact is, you could put that in there, it's just not going to change your formula. Okay? So I could say, okay, here's my defective, I'm choosing 0 from the defective bucket, but then from the not defective bucket, I'm going to choose 4. Okay? Does that make sense? Okay? So when I do that, this is the fraction you're going to get. Okay? So in all of these probabilities, here's the one thing I want you to notice. In a problem like this, the total possibilities is going to be the same in every problem. So it's the top number, the numerator, that's going to change each time. The total possibilities in the bottom is going to stay the same, choosing 4 out of the 24.
True.
Okay? So that's my reduced fraction, and that is my chances of doing that. Which, if you think about it, if 20 out of the 24 are working just fine, it's a fairly high probability that I'm going to pick one that's fine. Okay, 45%, 46%. It's a decent probability. Okay? Now, so do we think, let's look at C. The chances of choosing all of the defective ones. Do we think that's going to be higher or lower than this? Is it likely that I'm going to pick of the four that I pick? Is it likely that I pick the 4 that are broken out of the 24?
Not really.
Oh, think about that. There's only 4 out of 24 choices, which means what this means here is how many non-broken ones are we picking?
3. Oh, come on. 20?
0.
0. I'm not picking any broken ones. I'm only picking broken ones. So from our 2 buckets, we're picking all the defective ones. From that bucket of 4, we're picking all 4. From the bucket of 20, I'm picking none of them. So I end up with all of them being defective. Okay? Okay? So in this case, I don't have to worry about the number of choosing from the not defective ones. The ones that work fine. We're not picking any of those. We're only picking the ones that are broken. Because if I pick 4 out of 4, that's what that's going to look like. Well, what is that? What is this? 1. So now it's 1 over this 10,626. The ones that are not defective, we're not choosing.
What would you have it like that? And that would just be 1 though.
You could, yeah.
Why don't you have that?
It would be 0. This would be 0. You'd pick 0 of those.
Okay.
Because you don't have to, because we're not picking any of them. So if you really wanted to, these are, if the not defective ones were, there's those 20, we're not picking any of those. If you really want to include that in there, you can. Okay? It's still just 1. It's 1 times 1. Okay? So if you want to keep that, okay, we're selecting 0 from that bucket, you could put it in there, it's just not going to give you anything. Right? It's going to give you a 1. Okay? Now, so that decimal is that. So it is. It's very small. The likelihood of picking 4 broken transistors out of 24 is small. It's unlikely to happen. Okay? Now, let's talk about at least 1 defective. Here's what this means. Okay? We're going to sort of look at the situation. When we get that at least statement, that at least phrase, what we're going to be doing is subtracting from 1. Okay, so what is the complement of at least 1 defective? So at least 1 defective means there could be 1 defective, there could be 2 defective, there could be 3 defective, there could be 4 defective. So, if it's at least 1 defective, what are we ruling out? The situation where 0 are defective. Okay? So again, let's think about that. If it's at least 1 defective, So there, it could be 1 is defective, it could be 2 is defective, it could be 3 are defective, it could be 4 are defective. What it can't be is 0 defective. There has to be at least 1 defective. So what I have to rule out is B. I have to rule out this situation where none of them are defective, because that's not part of this. Okay, so here's what that's going to look like. I'm leaving that up there. I'm leaving B up there because that's the one we've got to rule out. Because in this situation here, none of them are defective. But in part D, we can't have that. We can't have a situation where none of them are defective. We have to have 1, 2, 3, or 4 defective, which means we get rid of this one. And so how we do that is we subtract it from 1. Because we're not going to find the probability of 1 defective and 2 defective and 3 defective and 4 defective and add them up. We're going to subtract the none defective from 1, and that's the at least piece. And anytime you see one of those at least problems, that's what's going to happen. You're going to take the complement of the event. Okay, well, we already figured out what the none defective is. Okay. Okay, we did that over here for part B, and most of the time when you have these parts like that, you will have calculated it earlier. Okay, so the probability then of getting at least 1 defective is just 1,927 over 3,542. That's reduced, okay, which is this number here, okay, or 0.544, which again is 1 minus this. Okay, so that's where that at least piece comes into play. This section gets tricky because of the number of piles or the number of buckets, and you have to determine, 1, how many are in each of those piles and buckets, and then how many you are choosing from each of those piles and buckets. So it's not going to be straight, simple one combination. Most of the time there's going to be multiple combinations, and you're going to multiply them together and have to divide by the total number of numbers. Okay, that's the difference between this section and what you did in 4.4.
Wait, so if we had like 3 piles, we just multiply all 3 together?
Correct. If you have 3 piles, 3 buckets, you choose from each of the 3, and you're going to have 3 different combination sort of formulas for each one. Okay?
Yes, sir.